Okay, hello everybody, and welcome to this second webinar in our Ocean Decade webinar series. Thanks everybody for joining today. My name's Neil Fletcher, and I'm Digital Media and Outreach Manager at EUMETSAT, and I'm here in Darmstadt, Germany. And it's a pleasure to be jointly hosting this session with my colleague from Mercator Ocean International, Fabrice Messel, who's the User Experience and Learning Manager at Mercator Ocean. So we're going to be doing a kind of double act today hosting. So it's going to be a really interesting session. So before we start, I'd like to thank the EU's Copernicus Programme for funding this webinar series, and also the co-organisers from the Copernicus Marine Service, from EMODnet, and from the Early Career Ocean Professionals group. We've got a really good team putting these webinars together. And I'd also like to acknowledge the support of the UN Ocean Decade Data Coordination Office, who've been helping to promote the webinars. Just before we start, a couple of points on logistics. We're going to be recording this session, and that's really because obviously not everybody can join at this time, so we'll be able to put it on YouTube afterwards, and you'll be able to have access to the whole recording and see everything then. So that's the first point. And then the second point is, if you have questions, please use the Slido link that we have, and then we can track all the questions there. And some of my colleagues can answer questions during the webinar. The link's just appeared in the chat, and then we can answer. And then at the end of the session, we'll have a Q&A part where we can go through some of the questions and try to answer as many as we can. So now, if we could go to the agenda, just wanted to quickly run through. So the aim really today with the webinar sessions is to try to help you access and work with ocean data in ways that will support the Ocean Decade. So, and in this webinar, we're really focusing on the challenges related to marine pollution, biodiversity, and climate change. And we're not going to be able to cover everything in one webinar, but hopefully some parts will be useful for you, and we'll give you some ideas and show you some new data sets that maybe you've not been aware of before. So we tried to put a program together to sort of show you some of the different types of data that we have, and then go into more detail on some specific examples. So we're going to start with Louis Demond from UNESCO, and he's going to talk about the UN Ocean Decade data strategy. And then we're going to have some short 10-minute presentations from some of my colleagues, EUMETSAT and CMEMS and EMODnet. And they're going to be talking about some of the data that you can use linked to the challenges on pollution and biodiversity and climate. And then after that, we'll go into more detail, and we'll look at some specific notebooks, one on marine heat waves, and Fabrice will show us a web application looking at ocean plastics and show you some of the ways you can access data through CMEMS. And then Matteo will talk about EMODnet and how you can access some of their contaminant data on there. So we've got a really interesting, exciting program, and I'm hoping we get lots of feedback and questions that we can help you with, and hopefully we can spark some new ideas and new ways of working with data. So now, if we could, without further ado, go to the first presentation from Louis Demond from the UNESCO Ocean Decade Coordination Unit. And he's going to talk about the Ocean Data Information Strategy.
Good morning, good afternoon, everyone. My name is Louis Demond, and I'm with the Ocean Decade Coordination Unit, sitting here in the headquarters of UNESCO in Paris. And I'd like to thank the meeting organizers for giving me this opportunity to talk to you a little bit about the Ocean Decade data and information strategy, update you on it, and as well as the implementation plan that we've been working on these last few months, and give you a bit of a timeline on when that will happen to hopefully set the scene a little bit for the rest of this meeting and this webinar. As you all know, the Ocean Decade aims to meet these 10 challenges that we have here on the screen and really find solutions for the sustainable management of the ocean and ensure we develop a truly sustainable ocean economy. And challenges 7 and 8 in particular are on collecting and sharing ocean observations and data and developing that digital representation of the ocean to really assist in developing these sustainable ocean management solutions, in assisting with decision making, policy making. And therefore, these 2 challenges really underpin many of the other challenges in that regard. Indeed, information and knowledge will be cornerstones of the Ocean Decade. This was already identified during the development of the Ocean Decade Implementation Plan. And achieving the vision of overcoming all of these 10 challenges really requires an enabling environment for a distributed, federated, if you will, ocean digital data and information ecosystem that connects across disciplines, across geographic boundaries, and must include frameworks, infrastructure, people, tools, and resources to making happen. So one recurring theme that we often hear is how difficult it is for ocean data users to find, to access, to use ocean data. Data sources are many and varied, but they are scattered in a sense and uncoordinated, and that's really hindering our ability to drive scientific research and find these solutions. So early on in the Ocean Decade Implementation Plan, the ambition was set to develop an ocean data and information strategy that would allow us to create this global data and information ecosystem. Within the Ocean Decade, there are essentially 2 groups focusing on data and information issues. The first one, the Data Coordination Group, which was convened in November 2022, was specifically convened to focus on developing that overarching vision and objectives for this data and information strategy. And then later on, a further group, the Data Strategy Implementation Group, was convened to really focus, once the strategy had been set and the vision and the strategic objectives, to focus on the implementation plan. And then the other group is the Corporate Data Group, which convened a number of different private sector industry organizations to discuss what are the barriers today for data sharing, for industry to share their data into the public domain, and really to find solutions around that. And we know that the private sector collects and owns vast amounts of ocean data, from bathymetry to physical oceanography to biodiversity data, and that information is often locked up, used once and locked up in hard drives, in separate networks, even in PDF reports. And so how can we're working with this group to figure out ways to resolve that and make that data publicly available. And then last but not least, the Vision 2030 process, which I'm sure you've heard of, which was a process of setting the ambition for each of the 10 decade challenges, has also provided an opportunity to really think about what are the priority data sets, the priority data requirements that we need and that we wish to achieve between now and 2030. So that will help guide both the work of the Data Coordination Group and the Corporate Data Group. So in April 2023, we published our overarching data and information strategy with the vision to put in place by 2030 a trusted, inclusive, and interconnected ocean data and information ecosystem, and one that is actively used for decision making to support sustainable ocean management. Now, this overarching strategy is also composed of 5 strategic objectives that focus on let's say the infrastructure that is required for this federated data and information ecosystem, looking at ways to make data more discoverable and more usable. Also, with a third strategic objective focused around how do we build trust in the data, the information, and the system itself, focusing on issues of quality, data provenance, terms of use, and so on. A fourth objective that is really focusing on prioritizing digital solutions that really will speak to and help us achieve these 10-decade challenges. And then last but not least, in order for this digital ecosystem, data and information ecosystem to thrive, we really need the people and the resources. And so that fifth objective is really about expanding, empowering that human community of individuals that are data literate and can help maintain and make this system prosper. So those are the 5 strategic objectives, and there is a QR code from where you can download an executive summary of the data strategy, and it is published in 5 different languages. Once the overarching strategy was published, we got to work on figuring out what is the implementation plan for this particular strategy. And what we came up with was, we decided to develop a series of instructions and to organize these different instructions according to the different phases of a project. So we have instructions that should be considered at the project planning phase, other instructions focusing, for example, on metadata standards and so on, that would focus at the data collection and data analysis phase of a project. There are multiple instances within the project lifecycle where data sharing will be required, and so we have instructions for that. We also have instructions for publishing, for data archiving, as well as some instructions, some recommended actions to put in place in order to build that digital literacy and change the culture towards valuing data sharing much more. So that's the way the document was organized. There's about 30 different actions. And the beauty of it is that an implementer can pick up the document, go through these different actions and figure out which ones are already in place in their organization, which ones are not, which ones are relatively low-hanging fruit to implement, or maybe the ones that are not so easy to implement because of lacking resources. So really a tool to help organizations figure out all of these things out. Each action is organized or presented in the same way for ease of reading. There's an action description, and each action identifies who the implementers should be, and also how to do this, right? And last but not least, the rationale. What is the reason for us to recommend this particular action? What is it based on? Are there studies or papers that we can refer to that address these issues? And so this is what it looks like in the report. That description, the list of potential implementers, and how to do it. So every action looks the same. And we've also thought about, well, who are the implementers? Now, obviously, this Ocean Decade Data and Information Strategy is initially targeting the leaders of endorsed decade programs, decade projects, but of course, we want to leave a legacy behind that endures beyond 2030. And so we've also thought about who are the individuals outside of the Ocean Decade that may be sitting in national oceanographic data centers or in some of the GDACs or are simply data publishers or data users. What are some of the recommended actions that are specifically, let's say, targeted to those types of users and implementers? So why should this matter to you? Well, there's a number of things that we need to think about. The implementation plan will really guide you and your data teams to concretely and meaningfully align your system across your organizations, as well as to others that may be contributing to the Ocean Decade, right? So that's aligning across your organizations and in that multilateral mission. It's also the other key aspect is that if our digital capacities are implemented using similar norms, which they would be if we all use this implementation plan, then we can then these systems can robustly and sustainably work together, and this will definitely help the Ocean Decades partnership thrive well past 2030. And this is an analogy that I picked up from one of my former colleagues, Terry McConnell, who was my predecessor in this role, in fact, in the Ocean Decade, who said sparkly fountains need robust plumbing systems, right? So the sparkly fountain here could be that end user interface, that end user application that you might have on your iPhone that will, warn you about potential harmful algal bloom, right? Well, in order to get that information in an accurate and timely manner, we need all of that plumbing, all of that infrastructure, the data, the data acquisition, the data curation, data management, the data analysis, and the data presentation in order to be able to meet that. And so this is what the implementation plan is all about. If we really want to connect all these different existing data platforms, data repositories, we really need to work together through this implementation plan, because it talks about this bit here where the real magic happens, so to speak, in that plumbing that is necessary for that sparkly fountain. And of course, let's not forget that in order to design that sparkly fountain, we need to do that in a co-design fashion, right, with the end users and the decision makers. So lastly, here's the strategy implementation plan and timeline. We've been working throughout the year on this, and we're coming up now in October, where we are ready with version 0 of the implementation plan. So we will soon be going out for a consultation and review. And in November, we will gather all that feedback, the comments. We also have a GitHub repository with some of that information there, so people can provide inputs through there. And we will compile and publish a final version in that November-December timeframe. And here is one last QR code. If you are interested in participating in this review process for the version 0 of the implementation plan, please feel free to submit your details. It's a very simple questionnaire so that we may reach out to you in due course. And so that concludes my presentation and the updates on the data strategy and the implementation plan. Thank you very much, and feel free to send me your questions or comments at that email address there. Thank you very much.
So thank you, Louis de Marne. So my name is Fabrice, so I'm very happy to be here with you today. Can you hear me well? Yeah. Okay. So thank you, Louis de Marne, for sharing this message with all our participants. Louis de Marne started this message talking about challenge 7 and 8 that are related to global ocean observing system and digital ocean. It can be confusing as this webinar focuses on challenge 1, 2, and 5, but the activities of EUMETSAT, EMODnet, and Copernicus Marine Service are completely aligned with challenge 7 and 8 to serve the implementation of solutions for all challenges. But now it's time to dive deeper into data and discover what kind of data can be relevant to your work, focusing on the 3 ocean decade challenges: understand and beat marine pollution, protect and restore ecosystems and biodiversity, and unlock ocean-based solutions to climate change. So EUMETSAT, EMODnet, and Copernicus Marine Service are 3 European services providing scientifically qualified marine products and services. Each has its own specific characteristics, and their catalogs are complementary. Each has their specificities, and you will see that with our next speakers. Again, as Neil said previously, if you have questions, please use Slido, and we will have a look at the questions at the end. So let's start with Hayley Erskine, lead marine application expert at EUMETSAT, the European Organization for the Exploitation of the Meteorological Satellites. Please, Hayley, the floor is yours.
Thanks very much, Fabrice. Hopefully you can hear me. Please let me know if you can't. I'm going to share my slides with you all. Okay, hopefully those should be sharing fine with you now. Yes, so as Fabrice said, today the responsibility falls to me to talk a little bit about, in more detail, about our data that we provide from EUMETSAT. If you attended the previous webinar, you learned a little bit about who we are as an organisation. I'll recap some of that, but then I'll also showcase some specific examples of data products and services that we offer and how these relate to the 3 challenges that we're particularly interested today. I'm happy to answer any questions about this, of course. Please do use the Slido. We can come back to those later. So in terms of EUMETSAT and marine data, you may remember from the previous webinar, if you attended, that EUMETSAT has 2 kind of core missions, if you like. One is to provide weather and climate data to our member state organizations across Europe, and the other relates to operating and providing data from satellites under the European Commission Copernicus Programme, which is actually where a lot of our marine activities sit, a lot of the work that I do. So looking at those missions, we fly the Copernicus Sentinel-3 and 6 satellites, and we provide the data from these in terms of ocean color, sea and soon ice surface temperature, and a variety of products derived from the altimeters. This data comes out basically as quickly as you can get it anywhere in terms of satellite data. So within 3 hours, our NRT streams are available. And it's also at the kind of native resolution of the instruments. So this sort of data suits applications really where you need the data as soon as possible and where you want to have highest spatial resolution and maybe some flexibility in your downstream processing. In addition to Sentinel-3, as I said, we have Sentinel-6, which is our kind of long-term altimetry climate relevant mission, measuring the sea level. And all of this data features very heavily in downstream level 3 and 4 products from the Copernicus Marine Service, which you'll be hearing more about later. You can just see on the right there to give you a bit of a flavor of all the different sorts of marine applications that our data from these satellites can be relevant for. And we'll talk more about those in the rest of this talk and in the rest of the webinar series. But beyond the Copernicus satellites, we also have data from our mandatory missions that relate to our sort of weather and climate monitoring work. Of course, a key thing that impacts the weather are the oceans, hence it's very obvious really that EUMETSAT should have something to do with the oceans. A lot of this data is processed into downstream products from our ocean and sea ice satellite application facility, the OCSAF, and they produce data products on sea surface winds, sea ice parameters, sea surface temperature, and radiative fluxes. Some of these products were also redistributed by the Copernicus Marine Service as well, so you'll probably see some of those in their catalog. So in terms of getting into the challenges that the UN Ocean Decade has summarized and presented to us, we've decided to undertake a bit of a mapping exercise to show how our data relates really specifically to each of these different challenges. And this webinar series is kind of part of those activities. But one thing we're doing in terms of resources to back all of this work up is develop a series of case studies, which are designed to show how our data can be used to meet each of the challenges. Each of these case studies includes a web article, which you can find on our website. You can read about data, how it's relevant for the particular application, but it's also supported by an interactive Jupyter notebook, and that's what you can see in the animation here is just one example. This provides a narrative explaining the data that's used and why, how it's relevant for the challenges, how to access the data, and then how to analyze and visualize it in a way that's appropriate for the particular example that we're interested in. And you'll see some of these both later today as a demonstration and during the rest of the webinar series. The notebooks are compatible with cloud services, so you can run them yourself without having to install things on a local computer, but you can if you'd like to. And this is an ongoing project. We're kind of using this as a focus point over the rest of the Ocean Decade to build all our case studies around the challenges where we can. And really, we're open to collaboration in these. So if you're using satellite data or if you're combining it with other types of data, and you'd like to showcase that in this kind of fashion, we'd be very happy to hear from you and work with you to develop more of these use cases. You can see the links in the chat relating to the articles and the code. So let's look a bit more in depth where we've got to with this mapping exercise, starting with challenge 1, which is one of our topics today, to understand and beat marine pollution. And I've just put in a few kind of examples here of what data can give us in terms of working towards this challenge, and ultimately then what society gets out of hopefully meeting this challenge using these data. One thing that from the sort of ocean color data that we provide you can get, and this is true particularly when combined with some of the data from the Marine Service and in situ, is estimates of coastal and inland water quality, as well as prediction of pathogen risks, so relating to certain types of pollution events. And this can benefit society in a number of ways, including reducing the monitoring costs associated with these hazards, and as well as assessing the impacts of different policy choices. It can also help towards operational planning for different marine industries, such as aquaculture, providing warnings for tourists, etc. And ultimately, to improved health comes for all of us that enjoy the marine environment, whether it relates to bathing water or food standards. One specific example we provide in our case study notebooks, and I won't go into these in too much detail because you'll see some of them demonstrated, is to look at how satellite data can contribute to monitoring algal blooms caused by excess fertilizer runoff, amongst other things. Satellite ocean color data can be used to monitor these blooms, and you can see an example there on the right. These are influenced, as I mentioned, by pollution in waters by agricultural runoff as well as other sources. And this is really important to monitor to provide warnings relating to water quality, as well as assessing the policy impact of what we're doing on land to see if we can stop these kind of events. The notebook in question shows how to access and process the satellite data on such blooms for specific images, such as this one, but also using some of the longer term data available from the Marine Service. In terms of challenge 2, which is to protect and restore ecosystems and biodiversity, the sort of data we provide from the satellites can help contribute, particularly when it's combined with others, towards long-term baselines of environmental status, information on chlorophyll and primary production, the location of fronts, risk from heating, presence of sediments, etc., as well as the detection of specific elements of biodiversity, such as phytoplankton functional types. And this kind of information can be used to help us to optimally site marine protected areas and to protect areas that are particularly important for biodiversity based upon the environmental needs of those species. It can help towards fisheries management, such as defining potential fishing zones. And it can also create efficient and appropriate marine spatial planning and environmental impact assessments, which are particularly important when we look at holistic management of the marine domain. One example workflow in our case study library at the moment is how satellite data can contribute to monitoring phytoplankton diversity. In this notebook and case study, we take a bit of a deep dive into how ocean color data works and how it can be used to identify different species of plankton based upon their signatures in the light field. Many of these different species have quite significant and important biogeochemical roles overlapping with other challenges, as you'll see. And the notebook shows how to access this data and also how to sort of tease apart and understand what causes the changes in the signal and how this is related to these different phytoplankton species. We also have an example of a workflow that's relevant under this on marine heat waves, which can affect marine biodiversity, but you'll see that later today in the demo. In terms of challenge 5, unlocking ocean-based solutions to climate change, there are a couple of different examples I wanted to point to here. We provide a lot of physical, oceanographic and atmospheric or weather-related measurements that can improve current, wave, wind and ice measurements and are a significant contribution towards model forecasts. And this gives us the opportunity to do things like optimize the siting for a renewable energy infrastructure, to improve safety at sea when relating to lives and infrastructure around extreme events, to plan in terms of coastal resilience for protection from storms, and to do things like produce efficient route planning for shipping to reduce fuel costs and emissions. Another thing that can be done is to understand the way that our ocean is taking carbon up, and this can be done via ocean color data, which gives us information on the different pools of carbon in the oceans. And this gives us an information on which processes and where these processes can be linked to carbon uptake in our oceans. One example workflow on that in our case study library is one here where we show how ocean color data can be used explicitly to describe the different carbon pools using different mathematical formulations for extracting this data. Other data can also be used towards monitoring of the system at large, but the data that we can provide offers insight into the sort of event scale dynamics, as well as contributing to understanding long-term trends when it's integrated with other satellites through the Marine Service products. The notebook shows how to access the data and also apply some simple algorithms so that you can learn how this works. That's a short summary of how our data can be relevant to the different challenges. I just wanted to finish here with pointing out once again all the different resources we have where you can learn more. Our user portal has all our different information about our missions and how to access the data, as well as links to our case studies. There's specific links for that as well as down in the bottom right there. But we offer a wide variety of other resources, code that supports the case studies, as well as other things, different training courses and video tutorials so that you can learn more about our data and how to work with it. And ultimately, if you need anything particularly from us, I can only recommend enough contacting our help desk, which is ops@eumetsat.int. Any questions you have, if you send one there, they'll get to the right person. So thank you very much. And yes, I remind you again, if you need to get in touch with us, ops@eumetsat.int is the place to call. Thank you very much.
Thank you, Hayley, for your clear presentation. It was very nice to see all your catalog of data related to these challenges. Let's continue our exploration of marine products catalog with Marine Delorme, Capacity Development Officer at Mercator Ocean International, the implementer of the Copernicus Marine Service, who will present relevant products and variables and use cases related to the challenges. Please, Marine.
Yes. Hello, everyone. Hopefully you can hear me and see my screen. So I'm Marine from the Copernicus Marine Service. Today, I'll provide an overview of the data available for each of the 3 ocean decade challenges we're focusing on this session. So quickly, the Copernicus Marine Service provides a wide variety of data from different sources like in situ observations, satellite data, and models. This data covers different timeframes, from historical data stretching back years to real-time information and forecasts for up to 10 days ahead. It also covers 7 regions, including the global ocean. At Mercator Ocean, through the Copernicus Marine Service, we develop advanced ocean simulation systems and numerical models using ocean observation data. These models help us describe, analyze, and forecast the ocean's physical conditions, sea ice, and biogeochemical state, whether at the surface or at depth, globally or in specific regions, and in real time or with some delay. We provide data on the blue, white, and green ocean. The blue ocean for physical data, such as temperature, waves, current, salinity. The white ocean for sea ice data, such as sea ice thickness, velocity, or temperature. Green ocean for the biogeochemical data, such as chlorophyll, pH, turbidity, and phytoplankton. So here you can see most of the parameters available for each of the color of the ocean. There is a single access point to the Copernicus Marine Service via the web portal marine.copernicus.eu. With a simple registration on the website, you can access nearly 300 free products. All the data is harmonized through the same format, which is the NetCDF format. In the Marine Data Store that you can see here, you can use filters like main variables, areas, or blue markets on the left of your screen to narrow down your product search. And so now, for each of the ocean decade challenges we're focusing on today, we'll take a closer look at the Copernicus Marine data that aligns with them. So challenge 1 focuses on identifying, mapping, and reducing both visible and invisible sources of pollution. So when we look at these, some key variables to consider are waves, currents, temperature, sea surface height, chlorophyll, and bioproducts that help track nutrient concentrations near river mouth. Here you can see on the right of the screen a snapshot of a global ocean physics analysis and forecast product showing ocean currents through the Copernicus Marine Service viewer. The data from this product is also available for download in NetCDF format directly from the Copernicus Marine platform. We also play a key role in plastic pollution research by developing global ocean circulation models. These models help us trace the detailed path of ocean currents and track where plastic debris travels after entering the ocean, but they can also help trace plastic pollution back to its original source. So here is an example of a solution developed using Copernicus Marine products. You can find this use case as well as the other ones I'll share today on the Copernicus Marine website. So this solution is called FML Track, and it offers an innovative way to help reduce floating marine litter in coastal areas. This service combines video monitoring, satellite imagery, and meta-ocean observations and models to track where marine litter comes from and where it's headed in the coastal ocean. It's a valuable tool for public administrations, cleaning companies, associations, and scientists to make informed decisions on how to track marine pollution. Challenge 2 of the Ocean Decade focuses on protecting and restoring ecosystems and biodiversity. So when we look at different marine ecosystems and species, there are many important parameters to consider, like micronecton, oxygen levels, pH, chlorophyll A, water transparency, temperature, ocean currents, salinity. And for the polar regions, any sea ice parameters are key to consider as well. You can see here on the right an example of a product that shows the mass content of zooplankton expressed as carbon in the sea for the global ocean. And in addition to these products and variables, Mercator Ocean International also publishes a weekly marine heatwave bulletin for the global ocean. So oceanographers analyze a range of data sets from observations to numerical models and forecast marine heat waves for the next 7 days. So you can find these bulletins on the Mercator Ocean website. And so here is an example of a solution that was developed using Copernicus Marine products. It's called the Wildlife Tracker for Oceans. It's a geo-framework designed for real-time monitoring of marine protected areas and the protection of marine megafauna. This tool helps marine scientists predict how different factors influence the migration pathways of these animals. Conservation organizations and policymakers can use these insights to develop initiatives to protect endangered marine species and assess the effectiveness of marine protected areas. So this software retrieves live data from Copernicus satellite for ocean biophysical data, such as sea surface temperature, chlorophyll A concentration, and zooplankton. Finally, for Challenge 5, its goal is to unlock ocean-based solutions for climate change. So these solutions can take many forms, whether they're nature-based, they involve ocean energy, or they focus on the interactions between the ocean and the climate. There are several important variables to consider, including, for example, currents, sea level, waves, temperature, salinity, sea ice, chlorophyll A, and acidity. You can see here on the right a snapshot of a wave analysis and forecast product on the Iberian Biscay Irish region. This data can be really helpful when thinking about developing ocean energy solutions and investing in technologies that can help reduce greenhouse gas emissions. So here is an example of a solution developed with Copernicus Marine products. Researchers from Taltech's Institute of Marine Systems have been exploring the potential of using seawater heat in Tallinn Bay to power heat pumps. So this innovative approach takes advantage of the relatively stable temperatures found in the deeper layer of the Baltic Sea, even during the winter months when heating needs are at their highest. So the success of Challenge 5 also depends on our ability to make accurate climate, ocean, and weather predictions. To achieve this, we need to deepen our understanding of the ocean and its processes. So each year, the Ocean State Report plays a crucial role in this effort. It offers a detailed look at the current state of the ocean, its natural variations and ongoing changes. A summary is also available for both the scientific community and a general public to help everyone understand the impacts of a changing ocean. So this year's 8th Ocean Report was published just a few days ago, and you can find it on the Copernicus Marine website. And finally, I just wanted to finish with sharing with you the various use cases that showcase how Copernicus Marine data is applied across the topics we'll be covering in this webinar series. These examples highlight the practical uses and the benefits of ocean data. So you can find this on the Copernicus Marine web portal. And for each use case, you'll find a list of the specific products used to develop the solution. So it's really interesting to look at these to also use as inspiration for your own work. And I also encourage you to check out the user corner on the Copernicus Marine Service website. It's a great resource where you can get a complete overview of the information and the tools available to both new and experienced users. If you have any questions, our support user team is here to help. You can reach out to them directly through email or chat on the website, or you can browse through 120 articles in the Help Center. Additionally, in the e-learning section, you'll find Jupyter notebooks, RStudio, and QGIS tutorials, along with video guides to help you access and download the data. So I hope this gives you a clearer picture of the free Copernicus Marine data related to the 3 ocean decade challenges we're discussing today. Thank you for your attention, and feel free to ask any questions during the Q&A session later. Thank you.
Thank you, Marine, for your presentation and very interesting use cases presented now. Last speaker is representing the next European service, Vicente Fernandez, science expert from the EMODnet Secretariat. Vicente, the floor is yours.
Sorry, I was muted. Yes, I was. Thanks a lot, Fabrice, and good morning and afternoon, everyone. My name is Vicente Fernandez. I'm a science officer at the EMODnet Secretariat. And here I would like to give you a very brief overview of how EMODnet in situ data and products are addressing especially challenge 1 about beating marine pollution. So this is more on behalf of the EMODnet chemistry experts. So in the first webinar, EMODnet was more extensively explained, but in a nutshell, I would like just to highlight that EMODnet is an operational marine in situ data product service funded by the European Commission, the Directorate General of Maritime Affairs and Fisheries. EMODnet is a network of more than 120 organizations and experts working in the field of in situ observations and in the development of products based on in situ observations, making them fair and interoperable with the rest of the world. And basically it provides easy and open access to in situ marine data, metadata, and data products for different domains. Ranging from physics, bathymetry, geology, biology, seabed habitat, human activities, and chemistry, which is the main focus here for challenge 1 on marine pollution. I would say also that EMODnet is a regional European node of the ODIS, the global ecosystem, data ecosystem. As one way of accessing all the EMODnet in situ data catalog is the EMODnet portal. It's a GeoViewer. You have here the link. I think it can be shared in the chat, which is a single point to access all the EMODnet products catalog for different domains, for different thematics. Here, I just point an example on the catalog and can be represented in layers on a map for the EMODnet chemistry, where you have in situ data products on beach litter, contaminants, eutrophication, microlitter, seafloor litter, and the distribution of in situ observations. I wanted just to invite you to visit this link and to take a look to all this full catalog of EMODnet data products. But here for this particular webinar on addressing challenge 1, of course, all the other domains can address challenge 2 and 5, but this is an example of contaminants of heavy metals in situ observations in Europe, where from the central portal you can visualize and you also can take a look to the metadata and download the data in different formats. But the central portal is not the only way to access the EMODnet in situ products. There is also an EMODnet Open Geospatial Consortium web services, including Jupyter Notebooks, where you can access all the EMODnet catalog. And this will be more further explained by my colleague in the second part of the presentation. You can see here the link where you can access all these OGC services, where all the EMODnet data products are open and free to access. So this is just what I want to say from the EMODnet in situ point of view for this webinar. So thanks a lot. I'll stop here.
That's great. Thank you, Vicente. There's a huge amount of information on the EMODnet platform to explore. Yeah. It's really interesting. Okay, so we've done the initial overviews of some of the different data types that we have available. And now it's time to move into the next section where we go into a more kind of detailed dive and start looking at some of the web access platforms and also look at some more detailed notebooks. So for this point, I'm going to hand back over to Fabrice, and he's going to tell you a bit more about the Copernicus Marine Data Viewer and the toolbox, and also look at the web application to track ocean plastic. So the floor is yours, Fabrice.
Thank you, Neil. So the idea of this session is just to introduce you all the material available on the Copernicus Marine Service first, to tell you that we try to facilitate as we can the access to the product and the information. That's why we have developed some tools like the Marine Toolbox, very useful to extract and download the products and use the products you need from the catalog of data. And then I will try to make a short demo of the viewer, because our viewer is very powerful to discover all the catalog of data and to display the data directly on the viewer and to start playing with data and extract some information. And then I will make a short demo on a demonstrator focused on plastic tracking, so based on plastic drift simulations. So let's start now from the website. So I'm going to be quick on this part because Marino already presented the use case page, also the user corner to access the different e-learning material, where you can, for example, find some e-learning material on marine heatwave. And then you can access directly to the Jupyter notebooks and a tutorial video related to this notebook. This is an article. You can find this article through the website in the user support part on the Copernicus Marine Toolbox. So this is very interesting to have this kind of tool because it simplifies a lot the access to the data. Sometimes it can be confusing. You can have different format to play with, and then thanks to this kind of tool, it's really easy to configure your code and extract the data, the subset of data you need. So you can have a look on this. It's very interesting for you if you have to play with the data and to play with a big amount of data, because there is no quotas on this kind of tool. And then this is the viewer, the Automation Pro viewer. So you can access directly from the homepage of the Copernicus Marine Service. So through this viewer, you will be able to see the complete catalog of the Copernicus Marine Service and make some filters and use the filters to find the relevant products for you. There is already some pre-prepared filters. And for example, so we are looking the seawater potential temperature at the surface. This is a 3D model products. As you can see, you can play with the timeline and change the dates you want to see, to display it on the viewer. You can also play with the depth, because this is a 3D model product. And for example, I can go on add layer. I'm interested in eutrophication and the concentration of oxygen in the ocean. I will choose the global products and the correct dataset. This is datasets with daily products, daily data. So I just have to click add map, and then you will see the data. So I need to change the timeline to cover a good period of data disponibility. And then you can play with the different color map, the opacity of the layer. If you want to see correlation between two different variables, you can also access to the product if you want to download the product, if it's the most interesting for you. As I said, you can play with depth here to see what's happened below the surface. You can click directly on the map and access some information about the data in this point in particular. You can draw areas, you can draw lines. So yes, you have to be patient. Sometimes it depends on your bandwidth, and it can take time today because I'm sharing my video. But okay, you can have some different measurements with graphs showing the evolution of your variable during the time, during along the depth, also with the profile. So okay, it can take a lot of time sometimes because I have so many demonstrators open on my window. Can be yes. So yes, it's just an overview of this powerful viewer. Don't hesitate to have a look on this viewer and play with the data and discover all the different data available on the Copernicus Marine Service. And to finish this demonstration, I would like to show you this demonstrator. This is a demonstrator based on plastic simulations. So there is 3 years simulations behind this viewer. And the idea was to show what you can really do with information, oceanic information like currents, and make new added value products like plastic simulations, and to exploit these simulations from a web application like this one. So it's not public yet because this is a proof of concept. This is a demonstrator. And so it's very simple. You have just to choose a region, an area of interest. I took Madeira here in the Ocean Atlantic. And thanks to the simulation, we can access the results of the simulation backward or forward. So it means that you can display the origin of the plastic during this 3-year simulation, or the destination of the plastic. So for example, if I come back at the beginning of the simulation, you will see that if you launch the simulation and you check where come from the plastic to Madeira, what is the origin of the plastic in Madeira, you will see that with a very young plastic litter, it comes from Madeira. And then after 1 year, you will see that plastic can come from Spain, can come from Europe. And if you go after 2 years of simulation, you will see that the plastic has traveled across the ocean, Atlantic Ocean, and come from the America. Here you can see. And so this is very interesting to see the origin of the plastic and to imagine what you can do in terms of political discussion with other countries, because this is we can imagine that it's a local problem, but this, if we want to tackle this kind of problem, we need to be all the countries around the table, because it's globally a problem, very global. And if I go on this option to track the plastic from Madeira, you will see the different tracks of the plastic particles starting from Madeira and goes through the Atlantic Ocean. Okay, we have developed this demonstrator just to show that to the policy makers that you can have some policy to reduce the plastic. So there is an option to make some reduction scenarios where you can choose the emitter, the region, which is at the origin of the pollution, and limit the number, the amount, the quantity of plastic from the coast or from the river, and see the impacts, direct impacts on the pollution in the ocean. So again, this is coming from simulation of plastic. So this is not observations. The simulations have initial conditions, which are estimations of the quantity of plastics from the different coasts and the different rivers. So it's very experimental, and that's why it's only used as a demonstrator, and it's not public for the moment. But it's a good example of what you can do with data, with simulations, to tackle a challenge and to exploit the data to transform this in information and to support decision making. That's it on my side, Neil.
Okay, brilliant. Oh, thanks, Fabrice. That's a really interesting presentation, and there's some very cool data access mechanisms there. And I really, the plastic one, you can really see the power of some of these modeling techniques and what you'd be able to do in the future. So, yeah, thank you very much. Okay, so now we're going to take a quick break for 5 minutes, and then afterwards we're going to be joined. Ben Loveday is going to be talking about marine heat waves. So please join us back at 3:35. Okay, welcome back, everybody. And now for the second of our deeper dives into some of these ocean access systems and ways of working with data, we're going to turn to Ben Loveday, who works for InnoFlare, providing marine training for EUMETSAT. And he's going to be talking about marine heat waves and showing us Jupyter notebooks and data access mechanisms to work with marine heat wave data. So I'll hand the floor over to you, Ben.
Thank you very much, Neil. I hope you can hear me okay. Okay, thank you everyone for joining me for this short demonstration this afternoon. We've got a fair bit to cover. It is quite in depth, but I'm hoping that the notebooks, so we've designed them, are self-supporting, and so you'll be able to kind of follow along with them at your own time if you want more detail on any of the points we're going to discuss as we work through. The first thing I want to mention is for those of you that haven't worked with Jupyter notebooks before, it's a nice way of displaying code, so we can mix live examples of working with data on the fly with narratives, pictures, interactive demonstrations to give you a more kind of rounded experience of what working with our data actually feels like, and to make it a little bit more kind of friendly as an interface. All of our code that EUMETSAT share for our training can be found through this platform, our GitLab platform called EUMETLab. I will share the URL at the end, but if you just put the word EUMETLab into Google, it will come up as the first hit. And if you want, once you reach this page, all of our training content can be found displayed thematically here. And I'm going to be working on what I find under oceans, ocean training, applications, and the repository I'm working with is called Ocean Case Studies. There are full instructions for how you actually work with this code on your local system or on a cloud system included in this repository on this page. Again, URL at the end. I just want to give you an overview of how you actually get to it and then sort of move swiftly on to the demonstration that I'm going to focus on, which is contained within this code repository. So I've downloaded this code to my local system. I've set it up as is detailed below, and I'm going to move straight on to actually looking at what options we've got and what data sets are in scope for us working with marine heat waves in general. I've fired up Jupyter Notebook on my local system, and the first thing I've done is I've opened this index notebook. Now, this index notebook actually refers to all the notebooks we have inside this repository. It's relatively extensive. Haley's already referred to some of the ones that we have here on algal blooms, on quantifying carbon pools in the ocean. We have a few on marine heat waves, and I'm going to be looking at actually 2 down here on sea surface temperature anomalies and on marine heat waves in the Mediterranean. I've already opened those up at the top, but if you click those links, then they will open these other little tabs. And that's where we can actually start to work with the data to kind of inform our analysis, so to speak. I'm just going to close a couple of the little sidebars. We've got a bit more space to work, and then we're going to start working through this notebook bit by bit. And I'm going to talk through the major components of what is available here. So at the very top of all of our notebooks, you'll find all these buttons. This allows you to open more contextual information on the data that's available, how you get the code. And there are some other options for launching this code in different places, either on remote cloud systems like Binder or Wekio, or you can feel free to work on any remote or local system that you have access to. And all of this code, for those of you who are familiar with code, is written in Python. Okay, so we start off, what we're going to do is we're going to take a very, very short 5-minute step back from marine heat waves and talk a little bit about sea surface temperature as a fundamental parameter first. And the reason we're going to do that is, although sea surface temperature sounds like it's a fairly simple thing, it is in fact incredibly complicated and varies a little bit depending on who you get the data from. So my name is Ben. I work for or on behalf of EUMETSAT. So I deal extensively with our sea surface temperature catalog. And this is data we describe as level 2. Which means it comes directly from a single satellite. It is in the highest quality that we provide, but it's relatively complicated data to work with, and it's on the instrument grid. What we do is we take all of this data from all of these satellites at level 2, we combine this into one unified product, and that tends to become something we call level 3 or level 4. And that is typically what's distributed through the Copernicus Marine Service, which Fabrice gave you a nice overview of, and Marine as well earlier. So there's a bit of a difference between the type of data sets. Both have advantages and disadvantages. We're going to focus a little bit more on the level 4, but we're going to look at both data sets and how you get them in this notebook. So we start out the notebook and we do a brief description or a brief overview of what I just said, differences in data sets, differences in how we actually measure sea surface temperature, which is the key parameter from which we actually derive marine heat waves. It is possible to derive them using subsurface temperature records. And actually, sometimes subsurface temperature heat waves do show greater longevity or even intensity than we can see at the surface. But the subsurface records don't give us the same broad overview that obviously the satellite picture does. So in your own time, you might want to read a little bit about this and learn a little bit more about sea surface temperature and how it differs from product to product. And then we're going to move into actually getting our hands on the data itself. The first thing we're going to do here, once we get to this setting up our analysis stage, is we're going to import all of the Python dependencies that we require to run this notebook. They are all included within the installation instructions for this repository itself. So if you follow our instructions, everything you see here, whilst it made it like a long list, it's all included and will all be set up ready for you to go. Okay, and then we're going to move on a little bit further, and we're just going to create a directory to download our products into. We're going to define a couple of things that will help our plotting. And then key to this is we're going to go then and look at 2 data sets from the Copernicus Marine Service. They are both explained above. They are the Ostia multi-sensor SST products for the REP, which means it's the reprocessed products, the multi-year product. It lasts about 40 years in terms of duration. And we're also going to look at the near real-time product because that is what is most up-to-date and gives us the daily updated sea surface temperature field for our region of interest. And then we're going to define a couple of things with regards to how much data we want to get in terms of time and how much coverage we want in terms of space, and go away. And then a little bit further on, we're going to acquire this data from the Copernicus Marine Service. So if you are looking for an example piece of code for how you interact with the Copernicus Marine Service catalog via their data services that Fabrice gave an overview of earlier. This will give you a fairly comprehensive example of how to do so. It is applicable to any data set that is in the Marine Service. So you will need a Marine Service account, and this cell right here is just going to do the authentication for you. I'm not going to run this notebook live, but if you wanted to run these cells one by one, you can use this play button at the top or click in the cell and hit Shift and Enter. You must do so sequentially and fetch some data. And then what we're going to do with this data first and foremost is we're going to make a climatology. So we're going to take an average of every single day. And the day we're interested in actually is the 7th of October, 3 days ago. Just for the purposes of this demonstration. And we're going to make a daily average of what that sea surface temperature looks like for this region, the entire of the North Atlantic and the Mediterranean, or the northern North Atlantic. Anyway, if you have decent bandwidth, pretty much creating this plot is going to take you somewhere in the order of 3 or 4 minutes to do. It has direct access into the catalog. It doesn't download anything. It does it all into memory. So here you can see here is our standard, like fairly coarse pattern, because it is a 40-year average of all the data across the region. And we're going to define a couple of smaller regions in here called our level 2 region, where we'll get our high resolution products, and our TS region, where we'll get our time series from. So the reason we're going to look at this is because it's quite subtle how you define marine heat waves. It varies very much in how you define your climatology. I'm going to show you a little bit about how that subtlety works at the end of this note. So now we've got this this kind of broad scale pattern. Let's have a look now at what the latest 7th of October would look like when we compare it to the historical average. And it looks a bit like this. I've used a slightly different plotting package here because what this allows me to do is explore the areas a bit more thoroughly and interactively. So I can zoom in, for example, on the Gulf Stream separation around Cape Hatteras, and I can look at some of this crazy mesoscale variability that happens along our western boundary current. And we can explore a little bit more in general. And if we want to return to the big view, we can. But the broad scale picture to take away from this is on the 7th of October, which we wouldn't really think about as a particularly hot part of the year. We still have significant positive anomalies, so significantly warmer ocean than we would expect, both in the Western Atlantic and in the Eastern Mediterranean, the Black Sea, the Baltic Sea. Some of it is still 3 or 4 degrees warmer than we would expect for this time of year compared to the historical average. So there are a few caveats we have to consider when we look at the data sets in this way. The first is when we're going to define our climatology or a baseline we compare this against, is this the highest quality that we can make? Is this from a climate data record, preferably, or a long-term reprocess record? Good, but not quite as good, or from a near real-time record, not ideally the kind of data you want to work to define your baseline for your heat wave analysis or your temperature or your time series analysis. Now, we can look at the same pictures from level 2 data. This data I'm going to look at now is from the Sentinel-3 SLSTR, Sea Land Surface Temperature Radiometer sensor, as distributed by EUMETSAT. And now we're going to get that data from the EUMETSAT data store. Now, we're going to combine all the data together from 15 different granules of this data at high resolution. And we're going to pull all of that together and plot the same anomaly as above. And we can see a similar picture, but in higher resolution. You'd actually be able to construct this pretty much on the day or the day after this has actually occurred. So this is near real-time data compared to a climatology from a level 4 product. So there's a series of caveats where this is not valid, and I've listed them here. But you can see all this interesting structure around all the bays and all the different circulations in the Eastern Mediterranean. You can see the effects of some of these upwelling systems off the coast of Corsica and off the coast of Sicily, and the more dynamic expressions of circulation in the region. Okay, and this is for the same day. So there's some comparisons that we can do here between different products at different times. The last thing we're going to do in this little notebook is we're going to look at a time series of how the data looks from the level 4 products over the small TS series box I showed at the top. So this part of the notebook is going to manage all this data gathering for us. And at the very end of here, we're going to actually do a comparison to see over our small box in the Western Mediterranean, what does the annual time series look like from 1982 to 2021. If you run this notebook for yourself, you should find with decent bandwidth, the entire thing takes about 10 minutes to run. So you can get to this point with any region of interest that you specify in less than 10, 15 minutes for all the products. But we can see here that we have this black curve, which is our multi-year product. So this is the one that's been consistently reprocessed. It is a very high quality. And then in the red, we have the near real-time product, which is the one that is available up to date. And we can see actually we've got a little bit of a discrepancy between the two. We would entirely expect this to be the case. When we process in near real time, we don't have access to all the different supporting data sets that would help us do this analysis. And so this is just the guidance to show you that if you're going to work with marine heat waves and defining them for yourself, you should be very careful what you choose as your climatological baseline to do this kind of approach. There are products inside the Copernicus Marine Service that are suitable for both climatology definitions, mostly the multi-year products, the REP products, and those that will run right up to date, the NRT products. Okay, so it's a very short overview of SST and all its various different flavors and available data sets. Much more information in the notebook should you wish to probe further. The other notebook we're going to look at, which follows on directly from this one, is on marine heat waves themselves and how we define them. Just to give you a connection to the previous notebook, everything you should find in our catalog looks the same. The data sets are all defined at the top. They refer to each other as well as more resources and other case studies that we've done on heat waves. And they tell you what you will learn in each one. This notebook focuses more on the marine heat waves themselves. What are they? So essentially, they're generally defined as periods of abnormally high temperature relative to a historical average, with a degree of regional extent and temporal extent that allows them to be called a specific kind of entity in themselves. They have major impacts on tropical cyclone formation. They have major impacts on marine ecosystems, particularly coral reefs, but also with phytoplankton dynamics, seabird mortality, harmful algal bloom formation. They are a naturally occurring phenomenon. They are throughout the historical records, but given the last century's ocean warming signal, they have become more frequent and more intense than we've ever seen them before. So they're a focus of major study at the moment, both in terms of just sea surface temperature and the links between multi-faceted heat waves and how temperature, chlorophyll, for example, will interface or will play off each other with different lag times. In this notebook, we're going to use a package called XMHW by the Hobday et al. Or based on the Hobday et al. Paper. You can find links to all the primary references in our notebooks. And we're going to use that to look at the Mediterranean to see if we've got heat wave occurrences in the last 20 years or so. Spoiler alert, we do. So again, we have a significant amount of information telling you us about why we're going to use the data that we're going to use and what we're actually going to do. Going to set up our analysis here exactly as before. We're going to connect to the Copernicus Marine Service data this time, and we're going to use a clever little package called XCube, which will allow us to work with the data on the fly. So we define our bounding boxes and the years we're going to do our analysis over. And we're actually going to look at two different sea surface temperature data sets. One is the Ostia multi-year product that I referred to in the previous notebook, and the other one is another climate quality product from the CCI project, also available through the Copernicus Marine Service. I'll show you why towards the end of the note. So we're going to go away and we're going to go and interface with this with these data sets remotely. And the first way we're going to do that is I want to show you how to use the XCube viewer. And if you work through all these cells, it will show you how to do so. XCube is a fantastic tool. It allows you to directly connect to the Copernicus Marine Service data sets and then work with them on the fly graphically inside your own browser. So here I've just opened a direct connection to my Ostia product, and I can choose to step forward and backward in time to look at different days in this case, or I can actually click on the product itself, and bandwidth permitting for me, this will open a time series, which will show you the full interaction with that catalog, with that piece of data throughout the entire time. So a very useful package for you to understand how to use. As a quick demo of how to kind of interface with it here. We will use this kind of time series analysis as the basis for our marine heatwave definition at the bottom of this notebook. So scrolling on down, we're going to download this data now, and we can choose to download the data directly to our local hard drive if we so wish, or we can choose to work with it remotely by connecting directly to the service and reading it all into memory. I'm choosing to work in memory here, but depending on what system you're running on, you may have limitations to do so. I'm going to get two data sources, the two that I referred to earlier. One is the Ostia sea surface temperature data set. The other one is the CCI C3S temperature data set. We're going to load them all into our notebook environment. We're going to do a little bit of playing around with the data. So we're going to convert, for example, Kelvin to Celsius. And then we're going to submit it to this XMHW Python package, which is the scientific core of this notebook, which is going to go away and identify heat waves for us based on a series of parameters. And the parameters it's going to use to actually define this is it's going to set up our seasonal climatology. So basically the seasonal average across the entire data set. It's then going to apply a threshold to that, and it's going to look for times when the sea, excuse me, when the sea, when the sea surface temperature data itself basically moves through that climatology or that threshold for a significant amount of time, and therefore defines a heat wave. So all of these parts of the notebook do this analysis for you. And once you've reached the bottom here, we get to our kind of final crux of everything, where we can start to look at the two data sets we've got and what they actually mean for us. So the first thing we're going to do is we're going to look at the climatology we've defined for both of our sea surface temperature data sets. So we have the austere one in the blue and the CCI C3S one in the black. And this is, again, this interactive plotting approach, and we can actually see where they slightly differ through the year. They have slightly different ingested data, slightly different sea surface temperature definitions. So you can see they show a slight difference, but not anything too dramatic. And given the size of the heat waves we're going to be looking at, not anything that's going to really influence our analysis too much at this time. What we're then going to do is we're going to define our heat wave thresholds. So we're going to take one of our data sets, in this case, our CCI data set, and we're going to say, okay, if the black line is our climatology, what would be our 90% threshold that we have to actually pierce in order to be defined as a heat wave? And we can, again, move our cursor over this plot to see what the actual values themselves are interactively. And then as we move a bit further on, we're now going to get a little bit more in depth. We're going to say, okay, where are the places that this actually occurs, where our daily sea surface temperature is greater than our threshold, and does this qualify as a heat wave? Now, this is a bit more complicated, so I'm just going to zoom in here so you can see a bit more clearly where we're looking. So here we've got the black being our climatology, the blue being our threshold, and the red being our actual daily sea surface temperature. And you can clearly see examples where, for example, in 2019, this red peak on the day or over the course of about, or I'd probably estimate a couple of weeks, it's clearly higher than the threshold. Let's now ask the final question. Does that qualify as a heat wave via our definition? And if it does, what sort of strength did it have? What category? Move on to the final data set, and we can say, how many heat waves did you identify? And it's come back and it said, actually, I found 49 in the data set that you've supplied me here. They are either category 1, the least severe, category 2, the next least severe, all the way up to a category of 5. And we can finally, as part of our analysis, plot those. And we can look here, for example, hang on, let me just reset that. Look at our analysis. And we can see any areas here where we have this thick, dark red line. Let's zoom in a little bit further. Are areas where we have a defined marine heat wave occurring in this region, and we can get the specifics of that heat wave. For example, it lasted 11 days, had an intensity of 1, which is relatively weak comparatively. But if you look at different areas, you will find heat waves of categories 3, 4, 5 at various places in the record. And we can actually submit any sea surface temperature data set, provided it is appropriate for the time period in the region, to this notebook's analysis. So you should be able to customize it as you see fit for whatever kind of area and time you're particularly interested in. I have deliberately in this analysis restrained it to only use data up to 2021, which is the end of the climate data set. You can actually append the near real-time data set onto the end to work right up till yesterday, should you wish, but bear in mind this will be slightly lower quality, and you'll have to take your results with some degree of kind of circumspect thought whether or not you think that that's valid, but it's quite possible to do so. As I said, all of the notebooks are available at this EUMETLab, on this EUMETLab platform. You can find that at gitlab.int/EUMETLab. We will provide the links in the chat as well. If you have any questions about any of our notebooks, feel free to contact us at ops@eumetsat.int. If you have suggestions for new ones, we'd love to hear those too. You can explore all the EUMETSAT data, including the level 2 SLSTR sea surface temperature product I showed in the first notebook at the EUMETSAT data store. And you can explore all of the Copernicus Marine Service products that I've shown. There were 3 here at the Copernicus Marine Service data store, links provided for both. I'm sorry that was a whistle stop kind of run through what we've got, but hopefully you'll engage with the materials and you'll feel free to ask us questions about what you have.
Thanks, Ben. That was brilliant. It's a really very clear explanation of some very complicated information and some really powerful notebooks there as well for people to use and have a play with afterwards. So Thanks very much.
My pleasure.
And now we're going to the last of our deeper dives. We're going to hear from Matteo Mikos, who's from the EMODnet Secretariat, and he's going to go into a bit more detail about some of the EMODnet data access mechanisms and show us a notebook or two, I think. So I'll hand over the floor to you, Matteo.
Good afternoon, everyone. Thank you very much, Neil, for the introduction. I hope you can see my screen fine, and let's dive straight into it. So I'll be presenting a little bit about how EMODnet data can be accessed through Python and Jupyter notebooks programmatically in much simpler terms than what Ben just showed us, which was pretty amazing, I must say. So as explained by my colleague Vicente earlier, EMODnet in situ data is divided amongst 9 different thematics, spanning from biological data to data about human activities related to the oceans, to the ocean in Europe, and all of which is available through the online catalog. However, in certain cases, it's interesting to access this data programmatically. And this for EMODnet can be done using OGC web services through Python Jupyter notebooks. These web services are various different protocols defined by the Open Geospatial Consortium, which allow you to view, access, and retrieve geospatial data and metadata. They are fourfold, and the one you will use depends on the type of data you will be looking to access. So to start with, the web feature services, which are WFS here, are used to access vector data, which are stored as, for example, shape files or JSON files. The web coverage services are used to access raster data, such as geotiffs or netcdf files, as well as images. While the web mapping services are used to access visualizations of datasets, which is slightly different. So using web mapping services, you cannot access primary data, but just an image or visual representation of a dataset. Finally, you can use catalog services for the web, which are the CSW, to access the metadata available for any of the EMODnet datasets. And now, if you are interested in delving deeper into how to use all these services to access all the data from EMODnet thematics, there is a 4-part tutorial online on the EMODnet GitHub, which is organized as you can see on the screen, which will run you through how to use every service in much more detail than what I will present today. For the time being, though, we will focus on accessing web feature services containing the data on marine contaminants from the EMODnet chemistry thematic. To do so, similarly to what Ben presented earlier, we are using the Python library of OGC web services, which is called OWSLib. You can read all the documentation. I believe the links will be shared in the chat. They have extensive documentation on all the functions available through the library. But you can, using this library, you can then define the point of entry you want to access with the first line of code highlighted in the second cell here, in which you need to specify a URL for the web feature service you're looking to access. All these URLs are available on the EMODnet website in the web service documentation page online. And you'll see they are very varied depending on the the type of data and the thematic you want to access. Here we define the specific one for contaminants. And once that is done, we can list using the .contents method on the web service we defined earlier. We can list all of the available data sets through this web feature service. Then select one. Here I selected an aggregated data set of nickel concentration median values, which is a point data set of all sampling locations across European seas. And using the line of code you see on the right, we can access the metadata as a URL that will bring you online back to the EMODnet catalog using the .metadata URLs method. Once we have selected the data set, we can, by using the .getFeature method, we can load this data set as a JSON file, as is done in the first 4 lines here on top, and then save it and open it as a geodata frame. Once this is done, as you can see, your data is loaded into memory, and you can then play around with it, run simulations on it, modify it if you like, but also you can create visualizations, which is a bit what I'm going to show you now. For example, the dataset we just loaded looks like this once you visualize it at first. Now I realize this is a bit large, and you can't define, you can't say for sure what is present in this data because of the myriad of data points that are there. So we can also zoom into the data and get a better view of what is within the North Sea, for example. And this is one of the many possible visualizations and ways to access data for EMODnet. On this, I thank you very much, and I invite you all to the questions and answer session that will run right now.
Okay, brilliant. Thank you, Matteo. That was a really nice introduction to some of the ways of accessing data. That's really useful. Okay, so we've had all the deeper dive presentations. So now we have a bit of time to have a look at some questions. So I think we can probably pull up the Slido, and then we can have a look at what's come in. So we've got the first one is where can I access the tool to simulate the FML trajectories using Copernicus? I'm not sure. Maybe this would be a question for Aurora to answer if Aurora's here. Or Marine, perhaps.
Hi. Yeah, we added the link to the use case on the Slido. If the question was about this, I'm not entirely sure, but we linked to the FML track use case that I referenced during my presentation.
Yeah. Okay. Yeah, I can see it there, so people can access it and have a look. Yeah.
Yeah.
Thanks, Marie. It's a bit small, and I think my eyesight's not what it used to be. Thank you. And then I guess.
Sorry, I was muted, but yeah, Marine pretty much said it.
Yeah. Perfect. Okay, and then we've got how can I access the plastic tracker from Edito? And there's a reply to that one. Yeah, so it's not publicly available for now. And then we've got a question regarding Sentinel-3 and 6 and whether data is available on Google Earth Engine. And I think one of our colleagues has answered that and said, yeah, there's some of the data, but none of the ocean products are at present.
Yes, this was me.
Yeah.
I added
Sorry,
that. It's a common. It's right. It's okay. It's a common question we get. People are interested in that particular service, but generally speaking, and this goes for all data sets on there. They're not the same usually exactly as the ones that are provided directly from people like us. And certainly in the case of Sentinel-3, the only one that I'm aware of that's on there is the Ulchi top of atmosphere, the level 1 EFR product, which is not suitable for doing anything ocean related really, unless you're going to do your own processing down to get some information. And I can't tell you to what quality it's produced. We create an archive, we reprocess our data, we recalibrate. And it's hard to tell sometimes with these exactly how those data sets have been created, if they've been kept up to date. And they're also transferred off the normal instrument grid. So for some applications, it may not be the most optimal way of working. Depends on your application. But I'm always happy to talk to you about how to best get the right data set for your purpose.
Okay, thanks, Haley. And actually, while you're on there was a question about the EUMETSAT GitLab and if it's available after the webinar. And obviously, it's permanently available, and we're going to be continually adding content on there, I guess.
Yes, and if you have any feedback on this, please do let us know. The help desk contact is in all the notebooks, so you can always email us and say, this one I really like. Do you have any other ones that are similar? Or if you have other ideas for ones we should be doing or how we can improve them, we really love to hear about it. They're also all available as an MIT licensed piece of software, so you can also reuse them in any way you like. Of course, we also like to hear if you are reusing them because it shows that they're valuable to the community. So please do give us any feedback if you use them in your own training or other purposes.
That sounds good. And also there's a question about additional resources and notebooks related to the challenges. I think on the EUMETSAT side, you're working on some notebooks and producing them. Is that correct?
Yeah, maybe I can take this one, Neil. This is Ben from Innoflare by EUMETSAT. We have a number of examples for different challenges, ranging from sea level rise to tropical storm effects on the ocean sea surface, marine heat waves, all kinds of stuff related to ocean color data, algal blooms, harmful algal bloom detection, eutrophication. And we've got more coming shortly on a whole raft of different things we hope to kind of unveil over the coming weeks and months. So my advice would be keep an eye on the repository. It's looking to grow fairly substantially over the next 6 months or so.
Okay, thanks, Ben. And do we want to access? I think that one was answered as well. So I think are there any more questions that I can't see coming up? Somebody had asked about the notebooks and they're able to access them. So I think for the moment we've covered all the questions. So I guess if there are no more, then we can, if we move next to the slide to talk about the next webinar that's coming up next year, if we can just quickly put that image up. Yeah, basically the next webinar in the series will be in 2025, and it'll be on the 15th of January. And the topic's ocean-driven solutions for a sustainable economy and resilient communities. So we'll be working to put together another really good agenda for that and giving you lots of examples. And hopefully that will also help to inspire you to work with some of this marine data into the future. And then with that, I guess we can draw to a close because we've covered all the questions. We've been very efficient. So yeah, I'd like to thank all the speakers for the presentations, and like to thank everybody who joined us, and also like to thank also the company who are kind of the glue holding a lot of this together. So thanks to them as well. We've covered the next webinar. If you have any questions in the meantime, please have a look at the website that we've got for the EU data for the Ocean Decade, and we'll keep putting content on there. And we've actually put a resources page where you'll be able to find all the links that we've been using for the first 2 webinars. So hopefully that will be really useful. And then it just, I guess, remains for me to say, wish you a lot of success, and fun working with our data. And thanks for joining, and have a great afternoon, everyone. Thank you.